Hello and welcome back. In this video, we're going to apply some of the concepts that we've been looking at over the previous few videos. And we're in the subject of heat. Heat gets the symbol Q. Heat is an energy that is transferred due to a temperature difference, and it can be transferred either via conduction, convection, or radiation. Calorimetry is the study of what happens to a material when heat is either added to the material or removed from the material. And recall from the previous videos that if the material is not at a melting point or a boiling point, then adding heat or removing heat is simply going to change the temperature of the material. And that relationship is governed by Q is equal to mc delta T, where m is the mass of the material, c is the specific heat of the material, and delta T is the temperature change of the material. If instead the material is at a boiling point or a melting point, then the equation that governs the phase change for that material is Q, where Q is the heat added to or taken away from the material, is equal to mL. L is either going to be the latent heat of fusion if the material is at its melting point, or the latent heat of vaporization if the material is at the point of boiling. It's worth mentioning that the lowest energy state to the highest energy state for any material is solid to liquid to gas. So solid is the lowest energy state, gas is the highest energy state, and liquid in between the two. So now we're going to take these concepts and we're going to apply them to a problem. So the problem that we have is we have a 1 kilogram block of ice at minus 10 degrees C. Ice is water. So, and this is all going to be done at atmospheric pressure. So this is sea level dry air. So we have this 1 kilogram block of ice at minus 10 degrees C, and we want to know how much heat Q must be added to have steam or vapor at 110 degrees C. So here's our vapor, mass of 1 kilogram at 110 degrees C. So what I've done is gone off and collected some values from two different sources. One is the OpenStax textbook, and the other is just through a Google search. So the specific heat for a material depends on what phase that material is in. So what I've done is look through a Google search at the specific heat for solid water or ice. So through that Google search, I find that the specific heat for ice is 2,050 joules per kilogram per degrees C. And I just simply plugged in specific heat for ice, and I got this value. The specific heat for liquid water, I'm giving the symbol C sub L, can be found from the textbook, your OpenStax textbook, table 14.1. So this is 4,186 joules per kilogram per degrees C. The specific heat for steam or vapor for water, also I found through a Google search, is 2,010 joules per kilogram per degree C. Again, I simply plugged it into a Google search and found this value. The latent heat of fusion for water I got from the OpenStax textbook, table 14.2, 334,000 or 334 times 10 to the third joules per kilogram. The latent heat for vaporization for water, again from the textbook, table 14.2, 2.256 times 10 to the sixth joules per kilogram. The melting point for water, also I got from the textbook, table 14.2, 0 degrees C. The boiling point, also from table 14.2, 100 degrees C. And then I've put the mass down here so that I have all these values over here on the side. So we start off with this cube of ice at minus 10 degrees C. And we begin to add heat energy to this block. What will happen? Well, the temperature will change because it's not at its melting point and it's not at its boiling point. And the temperature will continue to change until it reaches one of those points. The equation that governs that, of course, is mc delta T. So this heat Q1 that I'm going to add to this material is going to correspond to a temperature change to get it to its melting point. It's currently at minus 10 degrees C. I need to change the temperature by 10 degrees C to get it to its melting point, which is 0 degrees C. The specific heat for ice, remember that's a different value than for liquid water, 2050. So I've got that written here as well. So Q1, the amount of heat energy I need to add to this block of ice at minus 10 degrees C to get it to its melting point is going to be 1 kilogram M times the specific heat of ice, 2050 joules per kilogram per degree C, times the change in temperature, 10 degrees C, is going to give us 20,500 joules. So I'm going to add 20,500 joules to this minus 10 degree block of ice. What will I get? I will get a block of ice at 0 degrees C. So now I have this block of ice at 0 degrees C. Now I'm going to add more heat energy to this block of ice at 0 degrees C. Well, 0 degrees C is the melting point. So when I add heat energy to a material at its melting point, it will begin to change phase. And the equation that governs that is the heat energy that is added is equal to the mass of the material that changes phase times the latent heat of fusion. So I want the entire mass to change phase, so I want the entire 1 kilogram here for the mass, times the latent heat of fusion. For the amount of heat I need to change the phase of this entire 1 kilogram block is 334,000 joules. So when I add 334,000 joules of heat energy to this block of ice at 0 degrees C, I get a puddle of liquid water at 0 degrees C. Now I have this puddle of water at 0 degrees C. What happens when I add heat energy to it? Well, it's not at its boiling point yet, so any energy I add to it's simply going to go into raising its temperature. So again, the equation that governs that is mc delta T. So Q3, the amount of heat energy that I add, is going to be the mass, and it's the entire mass, 1 kilogram, times the specific heat for liquid water. So you can see the specific heat for liquid water, 4186, times the change in temperature, and the change in temperature I'm going to want to have it go through is to reach its boiling point, which is 100 degrees. So 1 kilogram times 4186 joules per kilogram per degree C times the temperature change of 100 degrees C gives me 418,600 joules. Notice the kilograms cancels and the degrees C cancels. So when I add 418,600 joules to this puddle of water at 0 degrees C, what do I get? I get a puddle of water at 100 degrees C. So I've added Q3, and now I have a puddle of liquid water at 100 degrees C. Now I add heat energy to this puddle of water at 100 degrees C. Well, it's at its boiling point. So any heat that I add to it is going to go into changing the phase of it. I want to change all the phase. So again, the equation that governs that is MLV in this case, because we're now between liquid and gas, or liquid and vapor. So I want to change all the mass, that's 1 kilogram, times 2.256 times 10 to the 6 joules per kilogram. Kilograms cancels, and the amount of heat energy that I add, 2,256,000 joules, will take this puddle of water at 100 degrees Celsius to steam at 100 degrees Celsius. So when Q4 is added, now I have steam at 100 degrees Celsius. Now when I add heat energy Q5, what's going to happen? Now the temperature is going to change. So I want to change the temperature by 10 degrees C, because remember my goal is to have steam at 110 degrees C. I currently have steam at 100 degrees C. So I want to change the temperature by 10 degrees C. So when I'm changing the temperature, this is the equation mc delta T. So the mass times the specific heat, and now the phase of the material is steam. So here is the specific heat I will use times the change in temperature. So 1 kilogram times 2010 joules per kilogram per degrees C times the 10 degrees C increase in temperature gives me 20,100 joules. Notice your kilograms cancels and also your degrees C cancels. And so the total amount of heat energy that we need to add to get from a block of 1 kilogram ice at minus 10 degrees C to 1 kilogram of steam at 110 degrees C is going to be the sum of Q1, Q2, Q3, Q4, and Q5. So here it is down at the bottom. The total heat is going to be Q1 plus Q2 plus Q3 plus Q4 plus Q5. So when you sum up all of these heats together, what you get is 3,049,200 joules, or 3.05 times 10 to the 6th joules. So the answer to the question to get from minus 10 degrees C block of 1 kilogram ice to 1 kilogram steam at 110 degrees C is that I need to add 3.05 times 10 to the 6th joules of heat energy to this material. So this gives you a nice comprehensive example using all the different values that we've been introduced to. Specifically for water in this case, if we were dealing with alcohol or a different material, we would be looking up, these values would be different. They'd be corresponding to that particular material. So I think in the next video, we'll pick a problem from the OpenStax textbook and work through it so you get an idea of some of the stuff you'll see when you're solving problems. We'll see you next time.